So in this video we have a series parallel RC circuit, and so what we want to do is we want to solve for the total impedance and then the total current and also the total admittance, and find the currents through each of the branches of the circuit. So if we start by just kind of redrawing the circuit, so we'll just draw the circuit down here with our sine wave supply, and then we have the first impedance, we'll call this Z1, and we have the second impedance, Z2, and a third impedance, Z3. Alright, so looking there then, our first impedance is simply the resistance. Alright, so Z1 is simply 10 ohms with no phase shift. Z2 is 3 plus J4. And Z3 is the 8 ohm resistance, the inductive reactance, the second inductive reactance, and the capacitor reactance. So Z3 now is going to be 8 plus J3 minus J9, so that's simply going to be 8 minus J6. Okay. So these are our three impedances. What I did was I combined the series impedances in each branch, so we have three branches of impedances. So now we can just calculate Z total then using our parallel impedance formula of being 1 over Z1 plus 1 over Z2 plus 1 over Z3. And so we can just punch those in our calculator and come up with a value. So I'm going to use octave here as my calculator. And so I'm going to have Z1, so I'll go ahead and define Z1 now, is simply equal to the 10 ohm. Z2 is equal to 3 plus J times 4. And Z3 is equal to 8 minus J times 6. And so when we want to calculate Z total, that's going to be 1 divided by 1 over Z1 plus 1 over Z2 plus 1 over Z3. And so we get, as a result for that, right, we now have the equivalent circuit to be our AC source of 200 volts at an angle of 0 degrees, right, applying into this one total impedance, Z total here, which is actually a resistor of 3 ohms and an inductor of 1 ohm, right? So Z total, right, if we look at that, Z total was 3 plus J1 ohm. And again, if we're going to put that into Blackboard, we would have to put 3.00 ohms plus J1 0.00 ohms. Okay, and that would be the rectangular form of our impedance. And so we can convert that into the phasor form or the polar form. So I have a little function that does that for me, and we'll call it z total here. And so that gives me 3.1623 at an angle of plus 18 degrees. All right, so now we can find the total current. So we could come in here and find the total current. Okay. And they're also asking for the total admittance, y of t. So if you see up here, right, they were actually also asking for y of t. So let me just speak for a minute to y of t. So we know that the impedance, okay, the impedance to current flow, right, the opposition to current flow in an AC circuit is called impedance. And that is the reciprocal of the admittance. Okay, so the admittance is how easily current can flow. So if we look at Ohm's law, right, we can say that Ohm's law, that the voltage is equal to the current times the impedance. Okay, but using this admittance term here, we can actually say that the voltage is equal to the current divided by the admittance. Okay, so it's just, the admittance is just another way of writing impedance. And for parallel circuits, a lot of times they like to write those as admittances, because you can actually just, if you called this one here, this was the admittance y1, and this was the admittance y2, and this was the admittance y3. In a parallel circuit, the admittances y total, the total admittance, is simply equal to the sum of the parallel admittances. And actually that is just this equation right here, because if you rewrite 1 over y total, right, that's your z is 1 over y total. I just wrote that over here. And then these guys are individual admittances, so that's like y1 is, I'm sorry, there should be a z total there. Y1 is 1 over z1. Y2 is 1 over z2, and y3 is 1 over z3. So you see, it's really just rewriting the admittance in another form. But with parallel sort of circuits here, a lot of times people like to play with this admittance term instead of the impedance term, because they can just kind of go, okay, well, you know, that and that and that. But and that certainly works, because it really just is the impedance, or the reciprocal of the impedance. All right, so solving for the total current, we have our supply voltage E divided by the total impedance, okay, or multiplied, or you could write it that I total is E times the admittance. Okay, so the admittance total. So that's kind of what they're saying there. All right, but I personally just like to stick with my impedances. So if that works for you, just stick with that. And if they ask for the admittance, after you find the impedance, just do a 1 over and you've got the admittance. All right, so we can find this I total now. E is 200 at an angle of 0, because it's our reference. And so I total then is simply going to be 200 at an angle of 0 divided by Z total. And with the Octave software, it gives us that in rectangular form. and then we can just convert that into polar form. All right, and if you don't have this polar function that I build, all it is taking the absolute value of I total, comma, and then taking the angle of I total. But remember, the angle of I total gives it to us in radians, so we have to multiply it by 180 degrees and then divide by pi radians to get it. And so they gives us a current of 63.2 amperes. So if we were going to put it in Blackboard, we would use that. But in this case, I want to keep it up to 5 digits at the moment for accuracy. And then angle minus 18.435. So remember that this turned out to be primarily an inductive reactive. I mean, it had mostly resistance, but then it had inductive reactance in this circuit, which means that the current is lagging, and so that's the minus sign that we have here for our current. All right, so if we wanted to find the current for just one of these, now, this is parallel. So all of this is 200 volts. Okay, this whole node up here is all 200 volts. Okay, so if you wanted to find the current I1, you simply divide it by the impedance, Z1. And if you wanted to find the current I2, you simply divide that by the impedance in Z2, and same for this. And remember, when you're done with that, you could simply go through and add I total according to Kirchhoff's current law. The total current, which we have written right here, is equal to the sum of the individual currents. So we can go ahead and kind of just demonstrate that over here in octave. Okay, so in octave, remember I already put in Z1, Z2, and Z3, so I can therefore go I1 is equal to the 200 divided by Z1. And so now that's, again, there's just resistance in there, and the resistance was 10 ohms, so you have 200 divided by 10, which simply gives you 20 amperes. So again, if we were going to put that into Blackboard, it would be 20.0 amp, capital A for amperes. Okay. And so then we can calculate, like, I2 is equal to the 200 divided by Z2. And then we can calculate I3 is equal to the 200 divided by Z3. Z3, I made the Z's lowercase, so it is case sensitive. All right, so now remember that I total in rectangular form is 60 minus 20. And so if I take I1, add I2, add I3, we get 60 minus J20. Okay? And so that verifies Kirchhoff's current law, which tells me that my math must have been correct.